Hello, Ella. Can you hear me? Hello, can you hear me?
Yes, doctor, we can hear you.
Okay, sorry about that. I'm in a really bad place, but let's see how much studying we can do. If it becomes, I think my environment will soon become a bit noisy. I'll get feedback from you, and if it's too difficult, we can call it a day. But for now, let us study. I'm going to share my screen, and we can start. Okay. So obviously we've been looking, last time we were looking at the propagation loss that is involved in transmitting to the satellite. And really this is the simplest propagation model that you can come up with, because luckily when you're on the ground, you can see the satellite. So that is what we call free space propagation. And we looked at some, yeah, we looked at how that would work. I just want us to continue with that. Let me just get my pen working, just a moment. Okay, just get these guys join. Right. So I want us to go through these equations again because they are quite important. And basically, when you have your, is my pen working? Pen is not working. Right. Okay, so you have your satellite up here, and then you have Earth. You have your Earth station there. This transmission is in free space. As you can see, it is all free space. Obviously, free space doesn't mean a vacuum. There are things that are in free space that can block the signal, but we'll be going through those in a moment. And when you're transmitting back down, also this is free space. Okay, so your signal is going through free space. And so we use what we call free space propagation. And when we are propagating, the important factors are transmit power. So transmit power is the power that you transmit, not the power that you consume from the socket, but the power that goes out of the transmitter through the antenna. We have antenna gain. Okay. And then we have propagation loss. Propagation loss is the loss that you suffer along the path. And sometimes you can call it attenuation. So the signal is attenuated. Now, in general, this free space propagation, what we are interested in when we do propagation is what power we receive. Because you know that there is a power that you can receive that is not good enough. My network problems this morning, for instance, can be traced to that concept. If your signal that you receive is not above a certain value that we call a threshold, then you're not going to communicate. So we want our power received, which I can call it power received, to be greater than a certain threshold. Okay. And this threshold is usually called, yes, and this threshold is called the sensitivity. You can call it the sensitivity, but we are going to be looking at those concepts in more detail. Okay. Now, pen is playing again. Right. Okay, again. So now that means that the subject of our equation should be the power received. It is the one that we are interested in. And that is the subject of the transmit power, the antenna gains. In fact, we have two antennas, one at the transmitter, one at the receiver, and then the attenuation that we suffer along the path. The attenuation is really the more complex thing here, because usually you know the antenna gain and you know also the transmit power, but attenuation can be quite complex, and as we are going to see in a moment. Now in this case, this is called the uplink and this is called the downlink. So the link from the earth station to the satellite is the uplink, and the earth station, sorry, the satellite here is, we call them satellite repeaters because they receive a signal and rebroadcast it. So there will be a gain here, we can call it GT, that is the gain of the transmit antenna, and the gain of the receive antenna here. In this case, it is the satellite. Then we would have the gain of the transmit side of the satellite and the gain of the receive side of the satellite. Sorry, of the antenna. So you're looking at these links in totally different ways. The other concept we have here is that we have PT. PT, here we are going to have PR received. So also the signal that from the earth station, when it reaches the satellite, it should be at least above the threshold. And then what the satellite does is it gets that signal through the transponder and retransmits it with a certain power PT. It might do some processing. Maybe it will certainly amplify it. It might reduce the noise. It might regenerate it, like in digital systems, where it actually decodes and regenerates a new signal. But when it transmits it down towards the earth station, it will arrive with a power PR. So when we are doing free space propagation, I think Era keeps dropping off. Maybe she's having some issues. When we talk about free space propagation, we don't only talk about it in the concept of satellites. It's in satellites. It's in WiMAX. Okay, so WiMAX systems. We used to have WiMAX here in Uganda. I don't know if we still have it. It's in also microwave links. Microwave links. These can be in, for instance, MTN, Airtel. This is how they do their transmission. So every site must see every other site, and the signal is line of sight. So, you know, all these are really line of sight, which you can call line of sight. Okay. And also in other cases. So even in Wi-Fi links, for instance. Now, PR, generally, according to free space propagation, is equal to PT. You should get this equation in your minds. Maybe since you are computer engineers, it may not be, you know, your source of income. But I've had this equation in my head since my 4th year. GT, GR, lambda over 4 pi d squared. And usually with PR, we usually say that it is PR D. That means that PR is a function of D, but in fact, it's not only a function of D, it's also a function of frequency and all these other factors. But with distance, I know if I'm this far from the state, from the receiver, sorry, from the transmitter, what is the signal that I'm going to receive? Now we know that lambda is equal to C over F. C is the speed of light, F is the frequency. So therefore, it's okay also to say that PR is PT, GT, GR. Since lambda is C over F, then you can say C over 4 pi D F squared. Okay, so that is really the same equation. Now it also goes without saying that when we say the power received, it is basically equal to the gains minus losses. Okay, and the gains include anything that is positive, which is power received, power transmitted, that's a positive, gain of the transmitter, and gain of the receiver. Whereas the losses include the attenuation. Now, if you look at this equation, therefore, you can see that this part are gains, meaning that this part has to include the losses, right? Now, so basically gains are the positive things that add up, give you power. So the power you transmit is amplified. It's not really amplification, but there is a way that the antenna shapes a signal, giving it more energy in a given direction. So that's what we call gain. And I'm going to be teaching these things in another set of lectures. But anything that like distance costs you power. So if you go longer distance, you lose more power. Frequency as well, and also the speed of light. So let's look at, let's continue our discussion. And please chip in if you have any questions at any moment, just please let me know. So we can therefore say that, let me also introduce decibel. Decibel is like a logarithmic term that we use. So you can say that x, a big X in dB, when I use these square brackets, I mean like, I don't mean a function, I mean like a unit. Okay, but we know dB is really not a unit. It's like it's not a unit. It's more like a state. So you can say that x dB is 10 log 10 of x. In this case, x is linear. So that means that if x is equal to 1, could be 1. X is linear. If x is in watts, like power, then in its dB form, we say it is a dB watt. That's what we mean. When I say dB watts, I mean that actually the term that is in dB is in watts, is a power, right? Because we know power is measured in watts. So if x is 1, let me say 1 watt, for instance, but even if it was just 1, the value would be the same, but when it's power, we just want to be specific that actually this is a power value in dB. Then that means that x in dB watts is equal to 10 log 10 of 1, which is 0 dB. So if I say that you transmit a power of 0 dB, I don't mean that your power is 0, because you can't transmit a power that is 0. 0 dB is actually equivalent to 1 watt. 10 watts is equivalent to 10 dB. You know how logarithms work. So that would be 10 log 10 of 10. Log 10 of 10 is 1, so 10 dB. 100 watts is actually equal to 20 dB, because you would have 10 log 10 over 100, which 100 is obviously 10 squared, and you would end up with 20 dB. So this is quite important, expressing things in dB. If you had 10,000 watts, this would be equivalent to 40 dB. So you can see that logarithms give us an ability to express large numbers in smaller values. I mean, 10 to the power 10 becomes just 100 dB. So instead of looking at these large numbers, you can express things in decibel. Now, we don't say dBs. No, don't say dBs in plural or decibel. We just say dB. Okay, don't say 100 dBs, just say 100 dB. Now that means that if I have my PR, D equals PT, GT, GR, and we saw that it was I think C over 4 pi FD squared. If I convert this to dB, it means that I'm going to have 10 log 10 of PRD now becomes PRD in dB is 10 log 10 of that, which is 10 log 10 of PT plus 10 log 10 of GT plus 10 log 10 of GR plus 10 log 10 of that term, C over 4 pi FD squared. Now this term is PT in dB. This is GT in dB. Because sometimes I give you the antenna, usually they tell you the antenna gain in dB. They don't really tell you the antenna gain in linear, and this is GR in dB. And so then we end up with PR in dB is equal to PT in dB plus GT in dB. You can, in general terms, like when you are doing your things, you don't have to put dB really. I'm just making it here clear for you. Plus GR in dB plus, this is the other term that we want to look at, 20 log 10 of C over 4 pi FD. Now I've moved this square and moved it here to make the 20. So that means therefore that these are our gains and this term constitutes our loss. Now let's focus on the loss term. That becomes 20 log 10. C is 3 times 10 to power 8 over 4 pi minus 20 log 10 of D minus 20 log 10 of F. The reason why these are negative is because they are in the denominator. Who can give me the value of this term? If you have a quick calculator, please calculate for me that. Does anybody have it yet?
It's 147.56.
Exactly, 147.56. So this is then what we have. It means that our PRD in dB is PT plus GT plus GR minus 20 log 10 of D minus 20 log 10 of F plus 147.56. So this is the gain and this is the loss term. Now you can, obviously we need to remember that this is in dB. We've moved away from an equation that was using multiplications here, this equation, to an equation that is now made up of additions. Now, when we say loss, what is actually the loss? Now, the loss, you need to remember the loss is already a negative term. That means that those now become positive. In fact, the loss in dB, if I ask for the loss in dB, you should write it as 20 log 10 of D plus 20 log 10 of F minus 1.7.56. So this is the loss, okay? But when we put it in this equation, we have got to put a negative here. So that becomes minus, minus, and that one becomes plus. Remember, these are in their SI units. So D is in meters, F is in Hz. Now we can re-express this. Let's just continue with this very interesting. I hope you are not getting scared of the math. Loss being equal to 20 log 10 of D plus 20 log 10 of F minus 147.56. Let me hope you are not getting a bit scared of this is all very simple math. Now, sometimes because of the nature of these values, we tend to express, if we express D in kilometers and F in megahertz. Sometimes you can even say, let me express F in gigahertz, because for instance, for frequencies in the satellite range, all of them are in the gigahertz range. So that if I say 10 gigahertz, already the equation allows me to just put 10 and not 10 times 10 to the power 9, something like that. So sometimes we want to express D in kilometers because these are long distances, and F in megahertz. If you use this first equation, this equation here, remember D is in meters and F is in hertz. But what if we wanted to express D in kilometers? This would now become loss in dB would now be 20 log 10 D in kilometers times 10 to the power 3. Okay, this term is equivalent to D in meters. Because D in meters, you see 1 kilometer is equal to 1,000 meters. So if I express my D in kilometers, I must multiply 1,000. It also goes for frequency 20 log 10. F in megahertz must be accompanied by 10 to the power 6 minus 147.56. So what you get here then is 20 log 10 of D kilometers. So this becomes 20 log 10 of D. This one is in kilometers. This term L plus 60. This becomes 60 is from the 10 to the power 3. So the 3 goes there to make 60, then log 10 of 10. Because we are multiplying, so we basically add 20 log 10 of F megahertz plus the other term, if we add it, is 20 log 10 of 10 to the power 6. And that 60 goes there to make 120. And then obviously minus 147.56. So if we want to express our distance in kilometers and frequency in megahertz, then our loss in dB, the equation actually changes to 20 log 10 of D in kilometers plus 20 log 10 of F in megahertz plus 32. If you add 60, 120, that's 180 minus that. That is 32 point, I think, 44 in dB. So this is another equation. You don't really need to remember all these equations. The equation you need to remember is the original equation that I started with, this equation. If you know this equation, then you can remember every other equation. Now, before we go to Let me see. Okay, so before we go to that, let me just open another couple of, and we do a few examples because all these equations are becoming a bit too many for you, I imagine. But I can assure you that they are not any difficult. Now let's assume that we have a geostationary geo orbit. We know that that geo orbit is at distance is 35 863 kilometers. That's 5. And this geo orbit, the gain of the antenna on Earth and the satellite, we can say gain of satellite is equal to 20 dB, and gain of the Earth station is maybe 30 dB. Now, because we are transmitting on the uplink, we can imagine that the Earth station has a lot of power capability. So let's say it transmits about 50 dB. 50 dB is a lot of power. That is 50,000. That is 100,000 watts. That's a lot. Let's make it 20, 100 watts, or maybe 30, 1,000 watts, so 1 kilowatt. Okay, so let's say 30 dB. Now, my question to you is, how much power is received at the satellite? Okay. That means PR at that point. Assume a frequency of 10 gigahertz. So in this case, you can use either this equation, or you can use the simplified equation where we already have our distance in kilometers and frequency in hertz, in megahertz. So I prefer to use the simpler one, which is my PR is equal to PT plus GT plus GR minus 20 log 10 of D in kilometers minus 20 log 10 of F in megahertz. Now you see here before it was negative 20 plus. This was plus. But now this side, instead of having a minus in the loss, we have a plus. So that means that here will still be minus 32.44 dB. Everything will be in dB. So that means we have our 30 plus GT is 20 plus GR. GR is actually 20. This is 30, that's 20 minus 20 log 10. Now D is in kilometers, so we actually put 35,863 minus frequency is 20 log 10. Frequency in megahertz, if this is 10 gigahertz, megahertz means that it is 10 to the power 4. Okay, because megahertz is 10 to the power 6. So 10 gigahertz is 10 to the power 10, and then minus 32.44. This becomes 6080 minus, this one is clearly 80, this term here, because of that 4, minus 32.44 minus 20, somebody can get me this one, 35,863. And then we have our PR in dB as, what does that become? Does anyone have it? Unfortunately, my computer is playing up, so is it negative 240?
Negative 243.53.
Okay, so this obviously, that and that go. Sorry. This one cancels that out. Then 20 log 10. Are you sure? Eh? Is everyone getting this?
Oh, I'm getting 123. Negative 123.53.
Yeah, that seems a bit fairer because this term is about maybe 90. So negative 90, because this is a 10th power, it's in the magnitude of 40 dB, so about 40 to 45 or something like that, times 2 is 90 plus 32 is around 120. So I think this is more accurate. I don't know, because this is positive and that's negative. So negative 123.53 can easily be received. Of course, I got these numbers from my head. They are just random numbers. But negative 123.53 can easily be received on a satellite. If you know about your phone, you know that your phone receives about 90. Actually, it is more in dBm. There is something called dBm. So negative 90 dBm is actually negative 120 dB. Okay, and so if your mobile phone, your smartphone can receive negative 120 dB, then it certainly, the satellite can certainly receive negative 123.53 dB very easily. We may have to look up the thresholds for the satellite. Let me see. Yeah. So that's okay. Now, all this is really beautiful. I love it. I love propagation, and as you can see, it is quite easy. Somebody is asking why we are using negative 32 instead of a positive. It's because if you notice here, we said that our loss in this case is 20 log 10 of D, 20 log 10 of F plus 32.44. This is actually the loss. So when you put it in the power received equation, you have got to subtract, meaning that all these terms actually become negative. Okay. Now I cannot see clear on my screen because those of you who know probably know that my screen usually plays tricks, which is why I have a monitor. And so if you want to ask a question, you could ask.
I have a question.
Mm.
Excuse me, doctor.
Yes, please.
Yes, I have a question. I'm asking,
Mm.
what exactly does gain mean? What's the difference between gain and power? What does gain mean? Like, for example, the gains, what do they mean?
Okay. That's a really good question. I think that's Gloria probably. That's a good question. So for me to explain gain in totality would probably take us half a lecture, and I will describe it during our time doing cellular networks. But in general, gain is not an amplification. It is not like power. So let me just use a very small description for the purposes of this lecture alone. So basically, if I give a signal like 10 watts to an antenna, let's say an antenna like this one, it will push the power. In antenna systems we call it radiation. So it will radiate the power equally in all directions, meaning that the signal will come out like a sphere. Okay. Now this kind of antenna is actually not is ideal. We call it an isotropic antenna, where the signal emanates from the antenna like in a shape of a ball. So for me, if don't look, if a person is seated is in this direction, all they see is that power. Okay, but remember, all this power has moved in all sorts of directions. So maybe for them at most they may see 0.5 watts. Somebody standing in that direction will also see 0.5 watts because the power has been radiated in all kinds of directions. Now compare that with another antenna like this one, where you give it 10 watts, and instead of spreading it in all directions, it spreads it in a direction like that one. Meaning that all the power that was going to go in these directions, and think of 3D, more of a sphere, is actually focused on this direction. This means that maybe a person who is standing in this direction will see about 9 watts of power, and a person standing in this direction may see 0.0001 watt. Now that means that antennas have an ability to shape the power that you give it and focus it in only the directions that you want. So if I'm doing a satellite, I'm not interested in my power going, if I'm focusing on the satellite in space and I'm an Earth station, I'm not interested in pushing my power everywhere. I want to focus it at the satellite where I actually need the connection. So that is what gives an antenna gain. It's not that it gets 10 watts and multiplies it by 2 or 4, because that would make it an amplifier. And an amplifier is not, we know that amplifiers have gain, but actually that's not how an antenna operates. An antenna operates by getting power and harnessing it and focusing it in specific directions. That means that it would have a gain over an antenna that radiates the signal in all directions. Meaning if I'm in the right direction, I can receive 9 watts of power, compared to if I was using the isotropic antenna and I would receive 0.5 watts in the direction I'm in, because that's what I'm interested in. Now, how then do you get the gain? So we usually, for you to get the gain of an antenna, you have to reference to the isotropic antenna. So if this is the isotropic antenna, and I'm looking in this same direction and I'm receiving 0.5 watts at a certain distance, maybe d equals 1 meters. Whereas in this direction at 1 meter, I'm receiving 9 watts. Then the gain of this antenna, the gain of this one is 1. Gain of an isotropic antenna is 1, because there is no gain. It just radiates everything equally in all directions. So there is no gain. But the gain of this one is then obtained by the power received at the same distance in the same direction compared to the isotropic antenna, which in this case would be 9 over 0.5, which gives it 18 gain, and a gain of 18. Gain does not have a unit, because we know that's power, so the unit goes, and we get gain of 18. But we can, of course, convert that gain into dB by saying 10 log 10 of 18, and we get some value there that then would be in dB. That's why I said at the beginning that dB is not a unit, because as you can see, gain is unitless. It doesn't have a unit, but we can express it in dB as we can any other value. So that gives you the concept of the gain of an antenna as opposed to the power. The power is the power that goes, that radiates, that leaves the transmitter and goes into the, usually you have a transmitter here, and you have a cable, and you have an antenna. Yeah, Gloria, you've seen antennas in the lab. You can go and have a look. So usually you have a transmitter and there must be a cable to the antenna. If there is no cable, it means that this antenna is attaching at that point, and that's still okay. Now, this is the power transmitted is the power leaving this transmitter, PT. And the power that reaches the antenna, usually there is a bit of loss through this cable, but we can look at these issues later. But at this point, we can assume that the 10 watts leaving here is actually the 10 watts reaching the antenna. So now the antenna will derive the concept of its gain by how well it can shape that signal in the intended directions. That's why we have two different kinds of antennas. We have the isotropic antenna. We have, this is usually called directional antenna. Not usually, it is indeed called a directional antenna because you can see it radiates the power in a specific direction. Other antenna, and the thinner you make that, the better, although it might give you challenges in deployment. Other antennas include omnidirectional. Omni is that you have your antenna here and it radiates power equally in the horizontal plane. So if I'm transmitting like FM radio signals, I don't know where my customers are, but I know they are on the horizontal plane or the surface of the earth. So I use an omnidirectional antenna so that it can radiate in all directions, but only in the horizontal plane. Because there are no people in the vertical plane, no people in the ground, and no people in the up there. The other case is, what if I wanted to cover, like in cellular systems, we have sectors. So I just want to cover 120 degrees of a certain side. In that case, I use, right now I can't see my screen, by the way. In that case, I use what we call sectoral antennas. They are not very directional. They can radiate a power through an angle of say 60, 80, 100 degrees. And so at the end of the day, it depends on the application, how you choose your antenna. But in general, the directional antenna is going to be better, because if I have an antenna that radiates equally in all directions, I have another antenna that radiates equally in the horizontal plane. I have another antenna that gives me a big, these are called radiation patterns. And I have another antenna that only focuses power in a very little, in a very specific direction like that. This directional antenna, as long as the power going in is the same, the directional antenna will always have more gain. Okay, so I hope that is very clear to everyone. And we are going to talk about this again. Felix, why does the negative mean that it receives less power? Not really. The negative is just because it's a loss. So that's why I said at the beginning that my power received are the gains minus the losses. And the losses include, the gains include GT, GR, PT. The losses are what we looked at as the propagation loss. Now later on, I mean, if this was a complicated wireless course, we would look at things like attenuation due to rain, attenuation due to gases, which is so-called atmospheric absorption, and we can add it in there. But in our case here, I'll probably just mention it and we move on. Okay. Now this equation shows you.
Doctor,
Yes, please.
just to interrupt you. So now what's the difference between GT and GR?
GT and GR.
Yeah.
The difference is that GT is at the transmitter, GR is at the receiver. So it is possible to assume that the gains at the gain at the earth station is the same as the gain or the antenna you use. If you use the same antennas at the transmitter and receiver, then GT will be equal to GR if similar antennas. But usually that's not the case. So for instance, the antenna that is used at the base station is not the same antenna that is used in your phone. The base station is a powerful station, so you can afford to have more power, you can afford to have bigger antennas. But your phone is a very little thing that you put in your pocket, so it needs a small antenna. So that's really the difference. We want to separate them because they are not always the same in all cases. But in some other cases, like if you are creating a Wi-Fi link between Makera and Kasubi, it is possible to pick up similar antennas and use them at both ends. That's okay. So then in that case, GT is the same as GR. If we are doing the uplink, then if we are looking at the uplink, I can't see where I'm writing, is your GT will be at the earth station, your GR would be at the satellite. And if you are doing the downlink, your GT now changes to the satellite because this is a new link, and your GR is now at the earth station. It is, I think, easier to imagine and infer from the knowledge we know that the gain at the Earth station is very likely higher than the gain at the satellite. Because at the Earth station, you can afford to have these huge dishes. I'm sure you've seen them, the big dishes, say at Impoma. But the satellite is a very small thing, the size of a small car, maybe a fridge at best. And so you're not going to burden it with big antennas. So in that case, we can assume that GR and GT are not the same. And in fact, GT is very likely to be greater than GR. But that's really the difference between these. The other thing I should tell you is that I'll be teaching a course on antennas briefly, but antennas have a property that we call reciprocity. This reciprocal, basically it comes from that English word. The reciprocity property means that an antenna is not designed to work at the transmitter or the receiver. An antenna can work at any side. If you are creating a link and I bring you a bunch of antennas, you don't need to carefully pick which one goes where. Any can go anywhere, unless it's a design decision. So an antenna that can transmit can also receive a signal. But in general terms, like in the case of satellites, we might design an antenna for the Earth station because we want it to be bulky for purposes of transmitting a lot of power. But we can also, then for the satellite, we are limited by the size, so we have to design a small antenna. But in general, but otherwise, in most systems, an antenna has the reciprocity principle, which essentially means that it can work as a transmitting antenna as well as it would a receiving antenna. Okay. Right. We've hardly started our lecture, but I think it was really necessary to go through these equations because I'll be giving you a number, and you can set for yourself some numbers, but I'll probably set an equation. Let me just set a number for you, because if we can know what power we receive, it means that if we know what power we should receive, which is sorry, the threshold. So I know that, okay, my threshold is maybe negative 150 dB. So if I need to receive 150 dB, and these are the antennas I have, how much power should I transmit? So you can actually also work backwards towards setting the transmission parameters. And if you know that maybe my transmitter already transmits 100 or sorry, not 100, 20 or 30 watts, and yet I need to receive this signal, and this is the distance between this receiver and the transmitter, then I should choose gains, antennas with specific gains that can push me over the edge, so that I'm able to receive the signal that I want. All this stuff we are doing right now, thinking through the parameters that we need to add, is called link budgeting. Okay. I can't see what I'm writing, but I hope that I'm writing. Link budgeting means we are creating a link budget. By budget it means you have money, you want to buy things. So if you are left with 10K, how much milk can you buy? So let's say that my PR should be greater or equal to negative 150 dB. And we can use from this equation that we did. If my PR should be, let me use the equation that we did. Okay, Mulongo. If my PR should be greater or equal to negative, because here we found that actually the PR is negative 123. So what if I needed it to be higher? And by higher, we know that the negative value becomes smaller. So if I needed it to be, say, negative 110 dB, I know that my GT is 30, GR is 20, same link. What is my PT? Okay, because now you can work backwards to actually design your transmission parameters. And I think that one you can definitely do. Okay, there's no doubt that you can actually do that, because all you need now is to say that PR, which is negative 110, should be greater or equal to PT, plus 30, GT plus GR, 30 plus 20, which is 50. And then we know that we subtract this, minus 80, minus 32.44, minus 20 log 10 of 3, 5863, which means that actually my PT you remember how they do if we move these things, you can move this side as you can do that equation. I've lost my screen again. You can do that that equation quite easily. Okay, so you'll be going through that. You can, I'll probably set you a number and share it with the class just for you to go through this. The beauty with this is that actually these are exactly the same equations that we would encounter when we are doing terrestrial microwave links. Okay, so these concepts do not change. They work in every situation where we have line of sight propagation. Let me also, any questions? Okay. If there are no questions, I like how we are moving. We are making sense. So now I'm going to access my slides on the phone and we try to go through them. I may not be able to write, but we will be going through. No, actually, these are not the slides. Sorry about that. Brian. Okay. Now you see this thing. This is actually the geostationary thing. If we are at 10 gigahertz, do we have 10 gigahertz? Yes, we have 10 gigahertz. We have a loss of about 204 dB. Does that make sense? We already did something like that. So if we have 20 log 10 of, that was 80 loss, plus, you didn't tell me what the 20 log 10 of the distance is. This term is 20 log 10 of 3, 5, 863 plus 32.44.
So the distance is 91.09.
91. This one, 91 point. Plus 80 plus 32.44. Does that give us around 204?
Yes, it gives us 203.5. When you round off, it becomes 204.
Okay, you know, yeah, that's around 203.5. So me as a as a teacher, I'm happy when I'm vindicated. So you can see that all the calculations that we've been doing are correct, because if we look at this book, you can clearly see that a satellite at that orbital height of 35,863 kilometers will have, you are always going to suffer a loss of about 203 dB. So if you already know the loss, you can work backwards to know what you need to transmit and what the gains should be, the gains of the two antennas, for you to be able to receive a certain power. The other thing you see here is that the loss increases with frequency. So at 1 gigahertz, or at 10 gigahertz, at 20, 30, 40, always the signal loss is increasing. The reason why that is that in general terms, loss increases with frequency, because as the frequency increases, the wavelength becomes small. And when the wavelength becomes small, there are certain parameters that we can talk about. Maybe I should have started with the wireless course, wireless selection fundamentals. I think from here we'll do the fundamentals. But when you have a signal with a small wavelength, when it meets a barrier, you suffer a lot of loss. Whereas a large wavelength might go just around that thing. So that's why in general terms,
Doctor, I think you've muted yourself.
yes, sorry for saying that. I don't know how that happened. Yes, so as the distance reduces, also the loss reduces. If you increase the distance of propagation, as you can see, the loss will increase. But really that comes from the equation where we said that loss is 20 log 10 of D plus 20 log 10 of F plus 32.44. Clearly, loss is direct proportional. Okay, not well, it is proportional, I should say. I think direct proportion mean because this is a logarithm, so there is that logarithmic relationship, but clearly with D and also with F. If any of these increases, so will the loss. Now, this is what a satellite footprint looks like. If a satellite is right above Uganda, I think this is in Central America, you will usually have most of the power right below you because the satellite will, if you have the antenna like this, I can't see, but it will usually pump power in that direction, and usually most of the power will be in the center. When we study antennas, this will be a bit clearer to you. But because the satellite is so far high, it is suspended much so far above the Earth, the loss is not so significant. You can see that right in the center, there is probably 2 or 3. I can't see the photo, but you can. There's probably 2 or 3 dBs compared to the outer edge of the footprint. That means if I'm in Uganda and maybe the satellite is above me, right above Uganda, I am not going to get much better performance or a much better link than somebody in Mombasa or in Juba, because of the nature of the fact that the satellite is so far high that there is no big difference between the link distances. The link distances will not be so different when I don't know, you know your things of Pythagoras theorem. You can go and do the hypotenuse and you see how it looks like. But the beauty of this, yes, so yeah, so it comes like this. So usually the antenna is like that, and the power emanates out of or radiates out of the antenna like that. So you can see that most of the antenna will be concentrated in this direction, but even there, you know, the power is still quite strong. And by the time, if you are here, yes, you get 36 dB watts, but you see somebody at the edge in California or Washington or wherever will get 32 dB watts, which is only 4 dB watts below where the antenna focuses. And then after this, as this becomes weaker, you need another antenna, you know, to take on the next, and another antenna, sorry, another satellite, and another satellite, and so on and so forth. So this is called the footprint of the antenna. Now here we see other attenuations due to atmospheric absorption. This is in the C band. It will be worse in bands that are higher than the C band. Let's see. Where is the C band? Yeah, this is the C band, around 4 to 8 gigahertz. So these performances will be worse when we are at higher frequencies, because as we said, loss increases with frequency. So let me just take you through this, and maybe we will stop there. We can look at this next week. Now you see we have something called rain absorption. Remember our elevation angle? We want our elevation angle to range from here, you know, to anywhere as big as possible. But if it is too big, also the coverage footprint becomes small. But we don't want it here in this region where it is ideally 0, but we don't want it there. You can see that everything just shoots up. And you remember the reasons why a low elevation angle causes problems. Now, this is atmospheric absorption. One of the main ones is that if you're at a very low elevation angle, your signal will spend so much time and distance traversing through the atmosphere. So that means you suffer more atmospheric absorption. There is rain absorption. That means your signal is going through rain and it gets absorbed by the water droplets. You can combine that with the clouds. The clouds also have a lot of rain content and they can absorb. That means water vapor that is hanging in space, sorry, in the atmosphere, has the capacity to absorb the signals, mainly because they are very small wavelength. Now, others are absorbed by oxygen particles. So the oxygen particles tend to be big and they actually cause a lot of absorption. So that is called rain attenuation, atmospheric absorption. And which one is in the middle? Can you tell me? I can't see it.
Fog absorption.
Yeah, fog. So fog is like mist. It is water vapor that is suspended in space. And so here they've tried to separate it from rain, but you can see the effect is almost the same. Rain is really deleterious when it comes to radio wave propagation, especially at high frequency. That's why when you are watching TV and it starts raining or there's a cloud cover, when you're watching BSTV or these Go TV things, the reception just disappears. The signals get absorbed. But also atmospheric absorption, and this is mainly due to oxygen particles, is also really deleterious. For you to reduce them, you go to a higher elevation angle. Even if we were to do 20 dB, so if we did, 20 degrees, if we did an elevation angle of 20 degrees, we don't even need to think about atmospheric absorption. It is really small. But here we still have some significant, almost 1 dB signal attenuation, almost 1 dB. Sometimes they give you this in 1 dB per kilometer. Now, this is not for the total distance. This is not for the total distance to the satellite. It's only for the total distance that your signal will go through the atmosphere in the case of atmospheric absorption, or a foggy environment for the fog absorption, or a rain cell for the case of rain absorption. Now, rain actually pours or rains in what we call rain cells. Okay, you can find a rain cell here, and so this is Chikoni. But people in Rwanda are outside the rain cell. So if I have my signal from, maybe I have this is Kasubi, and maybe this is Kororo, and I have my antenna going through the rain cell to Kororo, my signal, sorry, I'm doing maybe a terrestrial link, I'm only concerned about this distance. This is the distance over which I apply my rain absorption. I don't apply rain absorption across the whole link because clearly the whole link is not inside the rain cell. Okay, any questions before I stop? Any questions? If there are no questions, we can maybe just call it a day. But I'm probably going to set a question, but you've seen how I set question. I come up with random numbers and do the math. So you could go through the math as well. Just want to tell you that it is possible that I can bring these things. So for instance, I can tell you I can give you the original equation and I tell you to express the loss in maybe distance in kilometers, frequency in gigahertz. So do a bit of practice as you realize it's not really that difficult. The other thing I can do is give you the power received and I tell you and I give you the power transmitted and I ask you to give me the gains of the antenna that I would need to at least receive the signal, that signal, and so on and so forth. So yeah, so I think we can maybe stop here. We'll continue next week. I really want to apologize. I wasn't really unprepared. I was just in a different place and things didn't work out well. I'm thinking of a question I can ask one of you actually. Yeah, no, but I can't. I've failed to think of a simple thing that I can ask. So I think let's call it a day. Have a nice weekend, and we'll meet again on Monday. I just want to inform you that I put the videos back. Please remove them. I'll be removing them very soon. Okay.